Hello. I've been working on a project, on an LED-based project, probably not surprisingly. And I thought it'd be interesting to share kind of the design side and a little bit of the PCB, the printed circuit board design that I've been doing. I should preface this by saying I'm by no means an expert at this. So keep that in mind while you're looking at what I'm doing. Now this is a little LED I'm using. It's a little RGBW LED. So it has red, green, blue, and white, all on one 5mm square package. And each LED die will maximum at about 1 amp. So you can figure this is roughly, you know, with the voltages we're looking at, roughly a 10 amp LED. So 10 amps is actually quite a bit for an RGBW. Now, if we look at first how we drive this, it might be interesting to look down and we see, here we can see the forward voltages. So, and this is at 350 milliamps. It'll change a little at different voltages. At different currents. It doesn't really matter for this discussion. So let's see, red is about 2.25 volts, green is about 3.3, and blue and white are 3.1. And there's a range here. So the first thing you look at is, okay, you know, the simplest way to drive LEDs is just to use resistors. So I could just choose 5 volts as my supply, and then use a dropping resistor for each of these. Dropping resistor, a MOSFET to dim them, and then I'd be kind of done. And that sounds like a nice, simple way to do it. The problem is the amount of voltage we need to drop. So if I have 5 volts, and let's take the highest one. So 5 volts on green, so say green is about 3.3 volts, so we're going to have to drop 1.7 volts. And 1.7 volts at 1 amp is 1.7 watts. So it's 1.7 watts for green, 1.9 watts for blue and white, and then 2.75 for red. So what is that? 1.9, 3.8, it's like 6 or 7 watts. And 6 or 7 watts is a lot. And my intention is to have this in a pretty small package. So I would need pretty big resistors, and I'd need some way to actively cool them. I may need a way to actively cool the LED anyway, but that's really not that great of a design, and it wouldn't be very energy efficient. So what are my options? Well, what I really need is a constant current source. I want something that can put a full amp through these, but will only put an amp through these. And it'd be nice also if I had something that could do dimming. There are a number of different chips that I could use for this. I ended up settling on one from Powtech called the PT4115. There's the 4115, which does 1 amp, the 4115E, which does 1.5 amps. I don't think they're likely different or significantly different for what I want to do. And the nice part is they have a pretty small sort of component list. So we have power coming in, we need a capacitor in the middle here. We need a sense resistor, and this will be something less than an ohm. We have the LED, we need an inductor, and then we need a diode here. And the way to think about these drivers is don't think of them as LED drivers as much. Think of them as small switch mode power supplies. So a lot of what you want to think about when you're doing this are very similar to the kind of things you think about when you're building a switching mode power supply. And the other neat thing about this, it has a dim input. So you can either send PWM to it, and it'll just listen to the PWM, or it can also take voltage as an input. Now these come in a pretty small package. It's an SOT 89-5. So SOT 89 is the package size, and then 5 means 1, 2, 3, 4, 5 pins. And there's a ground coming out the back too. So this is what I decided to do. And the first step, first real step is, can I actually build this, and how much would it cost for me to build it? And in this case, I'm looking at doing assembly on JLC PCB, just because I found that oftentimes getting something assembled from their people is cheaper and easier than me getting the boards and doing the assembly myself. I can do reflow myself, but in this case, having someone else do it may in fact be cheaper. There's a possibility I may need enough of these that I want larger quantities. So what does that mean? Well, first I need to take this typical application circuit and draw it, and I'm going to use KiCad. I need everything to the right of here, from the capacitor to the right. This is just a full wave bridge off an AC input, and I'm not going to drive it off AC. And VN can be 6 to 50 volts on the E variant. I think it's 6 to 20 or 6 to 30 volts on the other variant. I'm going to choose 12 volts. So we're going to start by looking at that. So I'm going to take this and redraw it. So let's flip over. And here's at least the first part, or my first drawing of this. So this is the PT4115 in the middle. We have a diode going from the switch across to VN. VN power coming in, VN across to VN. We have the sense resistor between VN and CSN. And then finally, we have the inductor in line with the LED and coming back to switch. So the way you can think about it is power is coming in VN, it's going across this sense resistor. So that lets the circuit sense the current through here. So LED plus, and then on this side we have the rest. And switch, you can think of a MOSFET switching to ground. It's kind of the way it is. If you want a lot more details, that data sheet I showed, this data sheet here has a big section on operation description, which will tell you basically how it is. It has a nice block diagram here too that shows you how it works. And the other thing it has, which I didn't show, application notes and input capacitor selection, inductor selection, output capacitor selection, thermal considerations, layout considerations. All of these things are pretty important, and because this runs at a fairly high frequency, it's like a switch mode power supply. Layout matters, capacitor matters, inductor matters. So we need to make sure we choose the right parts here. So getting to that, what am I looking for? So C1, the data sheet says that C1 should be at least 10 microfarads. What I'm looking for here is a capacitor that's big enough to essentially get rid of a lot of the transients that are going to come from all the switching that happens here. And I also want it to be a low ESR, or low series resistance, because that's going to control basically how good it is at doing its job in this situation. So how I selected one, basically we flip back, and JLPCB has a big parts library. And I went through, and what do you know, I'm actually on this. So looking for different capacitors and looking and seeing what the trade-offs are. I can go look at the data sheet if I want. This one, oh, this is not the one I chose. This is a different one. This is a 10 microfarad, 16 volt. and I ended up going with a 33 microfarad 16 volt, similar one. So figure that out, find one that's available from the manufacturer I want to use. That's always useful if they actually carry it and actually have it in stock, and one that meets my requirements. So basically what I did is look at all of the 33 microfarad capacitors they had, find one that was a reasonable voltage. Since I'm targeting 12 volt as my drive, I went with 16 volt to give me some headroom, and then went through and found the ones that looked like they were the best choice, and kind of repeated that for the other components. For the diode needs to be big enough that it can carry the currents. So I did based on that. Similarly, this resistor needs to be big enough to take the supply current to the LED. So I'm targeting 1 amp across the LED. That means 1 amp across here, across 0.2 ohms would be 0.2 watts. So I went with a quarter watt resistor. It gives me a little headroom. I'm a little worried about that. But the next step up that I found were 1 watts, and those were a lot bigger, and they didn't fit layout very well. So we have that. We have the PT4115 in the middle. You can see something showing up here. And then finally, there is the inductor. And once again, inductor selection, like anything for switching power supplies, inductor selection is important. Basically, I need an inductor that will carry enough current that it won't be fully saturated. So when I found an inductor, 47 millihenry, and I chose 47 millihenry based upon the guide in the application notes, and based upon what I could get from GLC PCB's parts list. Because if you want them to build it, it has to be on their parts list. So I ended up with one that I think supports 2 amps. So that should be enough. 2 amps, have this, and this. So you can see I added some power connectors. So these will just be 1/10 of an inch single inline pin headers, kind of what you'd expect. There is 2 pin for plus and minus, 12 volts coming in. There's the output for the LED, and then there's control. Pin 1 of control is ground, as you can see here, and then pin 2 is a dimming input. So that's going to be the PWM input. Now, this is the basic simple circuit, but of course the LED that I chose has 4 different LED chips in it. So what I essentially did is draw this once and then cut and paste and add in four versions. So essentially we just have the same schematic. This top schematic's here, and it's just replicated 4 times. The only thing that is different is the dim control. So dim 1 goes to the first, dim 2 to the second, dim 3, and dim 4. Now nicely, the component count is low enough that there's 1 capacitor, 1 diode, 1 resistor, and 1 inductor, which means I can just number them in a way that makes sense. So these are all 1s, 2s, 3s, and then 4s at the bottom. So I went through this. Actually, I went through this a couple times. I went and did a quick design, and then went back and did a redesign to make sure I had the right component footprints. If you have the wrong footprints, bad things will happen when they try to build your board. Your components may not fit. Or if you're just ordering the board, it'll come back and the components will not fit. So that would be unfortunate. So I built all of these and made all the changes, saved it away, do the usual dance in KiCad. So first, assign the footprints, and then create the net list. And the net list basically is a separate representation of all the connections here, how everything is wired up. And we need that because that is what controls what connections we need for our design. And for this design, this is I've probably spent an hour or two doing the layout here before. Basically what I did is I drew the first part of the schematic just with one section, so enough to control one LED. And then I came in here and did the layout and played around with it until I was happy. And then I went and did went and drew the others, came back and then did the layout there. And I've been playing around enough. I got it enough that I could go and see whether I could manufacture it and about how much it would cost. So now I'm kind of in the middle of cleanup. And cleanup involves a lot of things. It involves, turn off a couple layers here. So if we just look at the layouts here, it's like making sure that I have space here and that I have a consistent layout from this one to the next one, to the next one, to the next one. Are they all pretty much the same? They actually aren't right now. And that's one thing that I can go and fix. And then you can see here, I have some actual layout issues. These are coming from the, go to the design rules checker. You run it and it's going to give me these. And basically the reason I'm getting these is because some of the tracks I have, which I had hidden, now don't actually go where they're supposed to because I've moved things around. So what sort of problems do I have here? So I want to get the layout at least similar going across all of them. And the other thing I want to do is I want to make sure I have good supply of both power and ground off to these 4115s, because that ultimately is going to control whether I get good behavior from the circuitry. So first, let's do what I was going to do first, and let's see if we can just kind of clean up the layout a little bit. So I already tried. These four should already be in roughly the correct left to right. If you notice, looking between, let's focus that spot there. Okay, there's a little space there. Here, there isn't. So I can M, hit arrows until I get a little space and hit enter. So I'm just kind of basically trying to move. This guy actually has a little too much. Enter. Now at this point you may be asking yourself, is this really worth it? And the answer is, well, maybe. You can essentially keep cleaning up your PC design forever. And rapidly you'll end up with kind of diminishing returns. And you can see what I'm trying to do is just keep all of these outlines, the chip, the resistor, the capacitor, the diode, and the LED. All of these I'm trying to keep from overlapping. Now the design rules would tell me if they were overlapping. And we can see that this guy's a little too far down. I like having a little space. You can actually overlay the lines, technically. If you look over here, it's one of my least favorite features. So in KiCad, I want to move. So I select and I hit M. And I can arrow. And arrow does exactly what you want, but you have to accept it by hitting enter. Otherwise, you're in mouse move and arrow move mode at the same time. I find this more than a little annoying, but that's just the way it is. So let's look at all of those. Okay, these aren't all perfect. Now, I do have the option, if I want to, I could, let's just play this, select, 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 right click, align, align to right. Okay, so that's going to align all of them to the right. Now, I don't remember which one it takes as the primary, but that should give me essentially all of these aligned correctly on the right side. And actually looks pretty good. Now, the question, one obvious question is, why am I putting these components so tight next to each other? Wouldn't it be easier if I did use more space? And it would be easier to do the layout if I used more space. But if you go back and you look at the application notes, the application notes very specifically say, keep these as close as possible. So basically what I'm trying to do is keep the layout of everything as close as possible. Now, the 4 layouts are identical except for one kind of ugly part. So you remember how I said we support dimming. And here at the bottom, dim 1, dim 2, dim 3, dim 4, all of those have to connect to the dim part of each section. And okay, this dim 4 one, that's really obvious. That's easy to get there. The others, yeah, not really as easy. So we kind of have to go up and what I elected to do, I wanted to have nice, easy connections from the inductors. So here's one lead of the inductor going to the LED. Here's the other one going off to the switch. So this alignment seems pretty nice, and I can have nice big traces. That's good, but that means I had to figure out a nice way to get those other pieces up. So we have to run these little small ones on the back and then kind of cheat them in between my different layouts. And it took me a while to play around and move these so that I had enough space to fit everything in and still have enough space for this. So I'm pretty happy with the layout. We're going to save that. The next thing I want to do, and since I've moved a bunch of things around, what I like to do when I've moved things around, I like to essentially tear up my layout and redo it. And you don't really have to do it, but from my perspective, I get better results and I'm happier. I'm happier with those results when I tear apart and redo. And sometimes I'll do that, I don't know, 3, 4, 5 times during the process. It just works better that way. So now by default, track size is pretty tiny here. You see that? Okay, now that trace, is that trace big enough to carry the current I want? I could go look and decide, but since I have space, I'm going to use traces that are actually quite a bit bigger. There's really no reason to limit myself to really small traces. Unless I need to, especially for the parts of this that are going to carry quite a bit of current. So now the dim inputs don't take much current at all. They're just really a signal path. So that I'm just going to do directly. Now you may have noticed here and in other places, I currently have 90-degree corners. And at this point, I'm going to leave them as 90-degree corners. I might come back and redo them as 45s later, but it's really not worth it at this point. So that has this whole section wired up. And I think, with the exception of ground, and for ground, ground is a different discussion. So what I originally did when I wired up was, I'll show you, just draw it in. So what I had, so this is the way it looked in my first drawing. So I have this ground bus heading vertically, coming off the two grounds coming in, heading vertically, and then for each of these, there's a pretty hefty trace that comes over and hits a ground here, and then it needs to hit a ground. Okay, really there. Okay. Don't worry exactly where those go right now because it doesn't matter. Maybe this one up here is a little better. Those traces are messed up because I moved them around. So think of a ground coming across. I need a ground here, and then I need a good solid ground for the chip itself. And so this is how I do the first thing. So ground underneath, and then via, ground on top, and then I needed to get past this chunk of VN. So once again, via to the back, come across and down. And that was kind of fine for a proof of concept. From an operational standpoint, it's not great. I'm limited by the current through the via here, and that makes me a little unhappy. And the other thing I'm limited on is from a power perspective. All I have is, for this chip to dissipate heat, all I have is just this little PC ground plane here. And I don't think that's enough, or it doesn't make me comfy. So what I'm going to do is I'm going to do a ground plane. But first I need to go and finish, clean up, and reroute. So I'm going to reroute these other ones so they look like this. And that won't take very long. So which is essentially just removing all the routing I did before. Missed one. So some of my best advice when you're doing design is do not fall in love with the routing that you chose. You really need to be willing to tear it up at least once, and sometimes you might tear it up 3 or 4 times and redraw, either to move things around, to fix things you just don't like. There are just a lot of different things you might do. So now we've done that, go back and start routing. I'm going to start with the small ones. Okay. Okay, those are the dim ones. And we'll start routing the other ones. Now that's something I'll clean up. You notice this V in here is actually multiple segments. It's not one, and you can see that isn't quite horizontal. And we're just going to be fine with that for now. And I'll come back and maybe do something about it later. Or maybe not. There's nothing that says that all of your lines and tracks need to be perfect. They do need to be functional. You can see that's where the old one was. So what I'll do is I'll tear up this track, realign these, and then draw a single track on top of it, probably. And how's that looking? One there. That's looking pretty good. All I have left. Okay, let's. Don't need that via. Don't really need that via. I want to make sure that everything here kind of looks the way I would expect. And let's save, and then let's run the design rules checker. And that's pretty nice. It came and it said, you haven't violated any design rules, which means most of my cleanup and getting rid of the tabs, everything is fine. So now we need to figure out what we're going to do about ground here. And generally, so what I'm going to do in this case is do a ground plane. Now, whether or not you need a ground plane is a deeper discussion. And there are a lot of low current, slow sort of circuits you're doing that don't really need ground planes. In this case, I want two things. First of all, this switch, the LED driver may run at a reasonably fast clock, and helps to have a ground plane for that. And I really want a ground plane for power to take some of the heat from these guys and kind of spread it out for a bigger space. Before I do a ground plane though, I need to have routing already in here because ground plane doesn't handle routing. So the question is, how am I going to get from where I want to be to that ground plane? Now, let's go back up and just look at this top one. What do we need? Okay, so I have a ground plane on the back. I need to get to the front, and I need to get a connection here. And then I also need to get a connection somewhere from this guy. Now I'm going to do some stitching, but I need to do at least one connection first. Now I actually have a couple options here. So just noting, I could come across here and then kind of try to sneak through here underneath the resistor. Kind of see what that looks like. And what I can do, I can take this guy, right click, and do break track. And let's see if I remember how to do this. Break track should give me a break wherever I click. That was strange. It's not what I expected. Okay, let's try it the other way. What if we came straight up here and then like that? Would give us the option of that. Okay, so that's really an interesting approach. Then let's lose these guys, lose the via, lose that little chunk. Now I should be able to go back to routing from here, come across, get right where I want, do a via, and then that's okay. So this I'm kind of happy with, even though I'm going to put a ground plane underneath. This is really kind of a pretty nice layout. I have enough space here that I think I'm fine with that. And the other option, I could have come through here, which is arguably maybe has more space, but could be maybe a little problematic. So we're going to go with this. So let's do that. Gonna do those 4 first. You see it wants me to, there's a break there. So once again, this is kind of the existing controlling my design. And I can move and fix things later. Right now I'm just kind of trying to figure out conceptually what I want to do. Okay, don't need that via. Delete that track. So you notice I can see how much margin I have here. So it's flashing where I'm violating the design constraints. So it's maybe a little tighter than I'd like, but not really terrible. Back to routing. Okay, so this is kind of where we are right now. I'm going to save that. And this is the sort of incremental sort of updates that I tend to like to do. Now, one of the things I notice here is this guy can probably move up a little bit. It would give me a little more clearance here, which would make me a little happier. And I have space to move him up and get a little closer to the LED. Here it's tighter, I need to move the LED up. And that's probably the next level of refinement. I'm not there yet. So, and you notice we have a problem here. The other thing I'll do, you notice the spacing doesn't really make sense. Whenever you put multiple pin headers next to each other, make sure the spacing is so that I could put 1, 2, space 1, 2, 3, 4, 5. So I could do a 5, 6, 7, 8 pin connector on that if I wanted to, rather than a 2 and a 5. So it's nice to have the option, and it really doesn't cost you anything. You probably notice that this guy is no longer in line with him, and we're just going to leave that for now. So next, conceptually, what do I want to do? I wanted to move on and show the ground plane. And the problem with the ground plane is, let's turn off the front plane. So the ground plane, this is ground, this could be ground planed over here. I'd have to avoid these guys, and I need to avoid these guys. That doesn't look like it's connected, does it? Oh, it is. No, it's just a little too high. So I need to avoid these guys too. So what I can do, we have this thing called a keep out zone. So over here you see add keep out areas. And keep out areas are used essentially to tell the system where I don't want it to put copper, even if it looks like I'm trying to. So what I'm going to do is I'm going to come in and essentially outline these dim. I want to keep out copper pores. I'll constrain it to horizontal, vertical, and 45. It's on the back layer, not the front layer. And then I can start drawing. So basically I'm saying don't give me any copper pore on this. And you can see it gives me this hatched layer. It's kind of a little hard to see. It's deliberately not any clearer than that so that it doesn't make the presentation too busy. So now that I have keep out layer, now I can do the copper pore. And the keep out layer is what makes the copper pore easy. So go over here. First of all, I want it to be on the back. So I choose back copper layer, then I come here and choose add filled zones. So we're going to do it on the back. I'll call the net name ground. I really don't need it, but we'll put it there. And I can essentially go around and draw the rectangle. And if I hold Control, that gives me verticals only. And there's the result we wanted. Now, that's actually pretty darn cool. Now, you look at this and you say, well, how can I work on the board when it's like this? And this is actually because we have two options. We have show filled areas in zones, don't show filled areas, show outlines of filled areas. Okay, so this is show. That's don't show, so I can't tell where they are. And this just kind of shows the outline. Now, I don't know if you noticed here, it did exactly what I would have wanted around the LEDs. So it knows essentially where the exclusion is around these footprints. So it didn't give me any copper there. These vias, of course, are into the copper layer, so that's good. And then we'll flip back here. So now I've gotten the copper there, and now I have, turn on front again. Now I've pretty much got the design that I want. For the most part. Now, the one thing I'm missing is this section here, the ground and this trace are the only things that are thermally connected. And that means if this chip gets hot, it can put a little heat here, a little heat here, and a little heat off there. But I have this really nice big ground plane, and I'd like to put some of the heat into that. So, how can I do that? Well, I have to remember how to do... I think I remember how to do it. So what I'm going to do is add some vias underneath the chip, and those will give me a conductive path. Conductive path for the heat to get from essentially the chip terminals underneath down into the ground plane. So how can I do that? Well, I can just come over here. We'll see if I remember how to do this. I can say I want a via there. Now my recollection, let's see if I remember how to do this. I can select the via, I can do right, and I can do create array. Horizontal do, count 2, and let's just see what we get. Okay, so that gave me an array. It's a little big. So let's do that again. Create array. Try 1 millimeter. You know, that's pretty good. So that gives me four vias through. I'll probably stick with that for now, and we'll kind of see what we get. Now, try to move them so they kind of are in the center. Oh, once again, I moved them with the keys and then came back to get me. So I have those vias. Sometimes it's called stitching. I can duplicate. That gives me another set. Zoom in. Duplicate. Another set. Duplicate. Another set. So how are we looking? Well, switch back to the front so we see the front. The design is pretty good. I'm certainly happier with it than when we started. I still have some layout issues. VN, these can probably be a little beefier. This is going to take quite a bit of current, and I'd kind of like it to be beefier. I'd like those to be cleaned up and look a little nicer. And I'm probably going to actually do a fill into these areas, just because it doesn't seem to make a lot of sense to have a loop here. Let's just come in and have VN across all of these. And then beyond that, there's a whole lot of trace cleanup that I want to do. And I'll probably go back and move this over and change the exclusion zone. There are all sorts of other things. Get rid of that. Before I do that, one other thing that's really useful. So normally all the tracks are shown as solid. And one thing that's really useful to do is flip this. And this says show tracks in outline mode. And what this lets you do is see how many individual segments you have. It's not uncommon when you're doing routing to have weird things show up. And so, like, very obviously you see VN here. You see that comes, and you can see, okay, this, when I routed, came across to there because that was where the two segments came across. And that's why these are angled. It just went to that sort of thing. It's also sometimes easier to see whether they're truly horizontal. If you zoom in, I can actually see this isn't. That may or may not matter. So that is a bit of design. I hope you enjoyed it. And I might come back and show a later version, and I might show what you need to do to take this design and actually send it off and get a bid on it and actually get it built. So, thanks for your attention.